Okay, now for part 2, still graphing, not yet to the ungraphing part. So we're going to graph these two that we see here. Now I would just like to point out before I scroll down that one thing that should catch our eye immediately is these two have the same degree. That means we're going to have a horizontal asymptote, but not at 0. And here we have degree 1 greater in the numerator than in the denominator. That means we're going to get an oblique asymptote. So that's something to look forward to. Okay, let's start with number 28. We want to graph y is equal to x squared minus 4x plus 3 over x squared minus 4x minus 5. Now the reason that these make an oblique asymptote at all, a horizontal asymptote at all, is that in the long run the things labeled x become x squared, the terms of highest degree, overwhelm just one factor of x and a 3. So that in the long run, this guy approaches, this arrow is a mathematical term, meaning approaches. It approaches x squared over x squared. And since the leading coefficient of both of these is 1, that means that it approaches 1, or y equals 1. So what we are saying is that this approaches this as x becomes very large, positive or negative. That's supposed to be an infinity sign there on the right. Okay, so we have a horizontal asymptote at y equals 1. And now I'm going to factor both of these. That's step 2 on our handout. We've determined the long-term behavior. It's a horizontal asymptote at the ratio of the leading coefficients of the numerator and denominator. And now I have to factor to find the zeros of both the numerator and the denominator. So I have x minus 3 times x minus 1 over x minus 5 times x plus 1. Okay, so that gives me my vertical asymptotes at x equals 5 and x equals negative 1. I know those because those are zeros of the denominator. And zeros of the numerator give me my x-intercepts at x equals 3 and x equals 1. And what happens when y is equal to 0? Let's look back at the very top up here for our answer to that. F of 0, that's my y-intercept, is 3 over negative 5. Okay, let's work with all of these facts to make a drawing. So, I have a horizontal asymptote at y equals 1. I have vertical asymptotes at y equals 5 and negative 1. X equals 5 and negative 1 is what I mean to say, of course. Okay, And I have zeros at x equals 3 and at x equals 1. Now, looking at each of these, looking at each of these zeros here, each of the factors here, I see that every factor is of multiplicity exactly 1. So that means that my asymptotes are going to go like either like this, up high and down low, or down low and up high on either side of the vertical asymptote. Okay, so let's also look back at the original equation here. In this original equation, let's think when x gets to be very large, I'm going to have something big and positive over something big and positive. Everything's going to be very big and positive, with the numerator slightly larger than the denominator. That means just a little bit greater than 1. That tells me, wrong way, that tells me that I'm going to be coming into my horizontal asymptote from above. Okay, if I do that, then when I run into this asymptote, I have to go vertical, like so. And when I run into this asymptote, I have to be negative because 5 was a zero of multiplicity 1. And I have to be negative here, going through this 0 at negative 3/5, because negative 1 is also a zero of multiplicity 1. So I have go-throughs on these zeros, again because they're of multiplicity 1. I connect the dots, and huzzah, I declare victory. Now let's have a look at what Desmos makes of this one. A remarkable likeness, isn't it? Okay, so good. Okay then, next example is this. Y is equal to x squared plus 5x plus 4 over x minus 1. Okay, now with regard to long-term behavior, we see a polynomial of degree 2 over a polynomial of degree 1, which means that it's going to look kind of like y equals x. But in order to know exactly where this oblique asymptote, for this would in fact be an oblique asymptote, meaning a slanted line, an oblique line that is neither horizontal nor vertical, in order to know exactly where that is, we need to actually do the division here. So let's do a little synthetic division. Okay, and so the synthetic division tells us that the actual thing that we have going on here, if we do the division, we would get y is equal to x plus 6 plus 10 over x minus 1. Okay, that's what this quotient actually is. But it's more convenient to put everything over a common denominator. So if we put everything over a common denominator and follow that where that needs to go, then we will get back to x squared plus 5x plus 4. If I did this correctly, which I think I did. Okay, so now, so what? Well, this is the equation of our oblique asymptote. Okay. We can also see we have no horizontal asymptote. You can have an oblique, but not an oblique and a horizontal asymptote. So looking at the denominator, we see that we have a vertical asymptote at x equals 1. And we have x-intercepts at, gee, we didn't factor that. So we still need to factor. That's x plus 4 times x plus 1. So we have x equals negative 4 and x equals negative 1 because this guy is x plus 4 times x plus 1. Okay. Let's take all of these facts and put them in a graph and see how that looks. Okay. I need an oblique asymptote at x plus 6. So this is a line with slope equal to 1 and a y-intercept at 0, 6. I also have a vertical asymptote at x minus 1. And I have y-intercepts at negative 4, x-intercepts at negative 4, negative 1. Okay. Okay, here with a bit of revision is I have this oblique asymptote at y equals x plus 6. The x-intercept of this asymptote is at x equals negative 6, and the y-intercept is at positive 6. Okay, and I have these two dots for the zeros of the numerator filled in, those zeros being negative 4 and negative 1. So, those tell me something about the rest of the graph. What did we say our y-intercept was? It's going to be negative 4. I don't remember if we did say. Okay, so negative 4 down here. Now, if I think about connecting all of these dots, I get something like this, with a big down asymptote next to x equals 1, and a big down asymptote next to that oblique line, and then up here I have its counterpart. Now the reason it goes like that is because at x equals 1 we have a 0 of multiplicity 1. So those asymptotes go in opposite directions. And here's how it looks on Desmos. Now, the black line here is the asymptote. And you can see the purple line here is part of the graph with the oblique asymptote. And I have to zoom out pretty far in this case to see the rest of it. But it's out there. Okay, so it happens that most of the cases of oblique asymptotes that we're going to see are going to look either like that or sometimes like this. So they're going across this space like opposite angles or something. Okay, I believe that's the end of this part.